Welcome to the Flare Build Podcast. Today's guest is Jerry Marino. Jerry got involved with the Bazel community just after it was open sourced. Early on, he open sourced rules and tools to make Bazel work with the iOS ecosystem. On GitHub, he's a maintainer of iOS build components and tooling, but his main focus is Rules iOS, a Bazel rule set for iOS development. Jerry currently leads the iOS Bazel build team at Square. Now, over to your hosts, Tatiana and Zach, the co-founders of Flare Build, the first consultancy and product-based company focused on Bazel.
Back on the podcast again with us is Jerry Marino, and again we're going to talk about iOS and Bazel, and really excited for today's conversation. And I actually want to start things off, though, before we get too deep into the technical weeds. I actually want to talk a little bit about Jerry's most amazing hobby that he has, which is flying planes in a way that is just blows my mind. So Jerry, if you don't mind, maybe tell us a little bit about what you do outside of work. It's got to be the coolest pastime I've ever heard of.
This is I guess a little known fact about me that you won't find anywhere else on the internet. I am actually a competition aerobatics pilot. So I fly airplanes competitively in a competition where you're graded against how you can fly the airplanes against basically a predefined sequence. And yeah, it involves flying airplanes upside down pretty fast.
Yeah. So in layman's terms, stunt pilot. Yeah. Absolutely amazing.
Exactly. Yeah. It's a federated kind of organized aerobatic stunt competition across the world. There's world contests, there's a US contest, West Coast contest, and yeah, we're just a bunch of people that love flying airplanes. We often don't refer to it as stunt flying because stunt has like a negative stigma to it, but we practice safe flying of airplanes upside down. It's probably the funnest thing outside of coding iOS build systems.
Oh my God.
Yeah, absolute adrenaline rush. Yeah, very cool. I wish I knew more so we could have a podcast dedicated specifically to this.
I know. We're so shocked and amazed that we don't have any comments.
Well, let's see. My friend Mark Pollard actually runs a podcast, which is called Fly Cool Shit. And that podcast is kind of around warbirds and the aerobatics contest. So if you want to learn more about it, I definitely plug his podcast.
Awesome. Yeah, I will absolutely add that to the list. That sounds very cool.
Yeah.
Yeah, that's amazing. So if I'm not wrong, you do some of the maintenance yourself on your planes. Is that correct?
Yeah, you can work on the planes. I've always been a gearhead. I have an A&P who I work under who is signing off any of my work that I do myself, and we kind of do it together. So it's totally copacetic. And yeah, I love turning wrenches and tinkering with stuff. Maybe there's some actual overlap, tweaking these kind of things and actually optimizing the performance.
Yeah, I think so. So how does working on the mechanics of airplanes, but how does that compare to the complexity of making the build system work at scale?
I mean, you basically just got to look at something a pretty face value and elemental level and kind of take it for face value, I guess. Maybe it's a very stoic look at it, but I feel like that's how a lot of this build system stuff is too, right?
Which do you think has more moving parts, Bazel or an airplane?
It's actually hard to say. I can't imagine how many lifetimes have been invested in making Bazel what it is today. If you look at some of the sub-components that we run in the build system, like LLVM, Clang, and the Swift compiler, programs in this build system has lifetimes invested into it in order to make it work. I would say that probably Bazel and the iOS build ecosystem has significant more lifetimes invested into it. But if you go back to the basics, hey, they have an internal combustion engine. They have the whole idea that you can fly an airplane and we're humans, not birds.
Yeah, absolutely. Cool, man. Well, that's awesome. I don't want to go too off in the weeds on that, but very cool. I got to wonder if there's footage of you doing some epic performances somewhere, but we'll figure that out after the podcast.
We can nerd out on that later. Yeah.
Very cool. So for today's agenda, really, we want to talk about, your journey in the earliest days of adopting Bazel for iOS, because as some of our listeners will know, you are definitely among the first outside of Google to really dive deep into making Bazel work for iOS. And Yeah, let's go all the way back to the beginning. And maybe let's talk a little bit about, at your former employer, what some of the background motivations might have been to start evaluating other tools, tools like Bazel. I'm sure you probably also maybe looked at Buck and some of the other things that would have been around at the time. So yeah, maybe we'll just walk us through what led you to take a look at Bazel initially.
So how far in the past are we going?
I would say like mid 2010s, you couldn't even build an iPhone app without Xcode because all of the code signing logic, all the bundling logic, the tool chains, the execution of these tools, the scheduling of these tools, the organization of these programs was all kind of defined by Xcode. That was the only really way to like build an iPhone app with open source technology. You're basically at that point in the industry, you were beholden to whatever Xcode would do. So people at that point had built all these different kinds of abstractions around Xcode. And that's what CocoaPods was. It was effectively Xcode project generator with a dependency management system bolted onto it so that you could structure your program however you'd like with these like pod spec files. And then that thing would generate an Xcode project and install the dependencies for you. You could kind of go away. And that was pretty much, I would say, the state of the art as far as I can remember it. Don't quote me on that. Basically, you were building programs with Xcode, and then there was these other ad hoc tools around that to kind of manage dependencies, project generation, and everything was set up in XConfig.
Gotcha. So mid 2010, pretty much everyone was using something like CocoaPods. There's also alternatives back then that people dabbled with. But yeah, so CocoaPods obviously kind of won out on
Carthage.
that front. Yep, Carthage for sure.
Yep.
Yeah, and so that's a good baseline. Other than that, I know like obviously there's other project generation tools that have come about later, but yeah, I mean you're right that back then there's probably not much else going on, right? Even like some of the convenience tools we have like Fastlane and stuff that didn't make an appearance for quite a few more years later. So
exactly,
CocoaPods is kind of the baseline, right? What anything else you were doing other than that might be worth noting?
Everything at that point in history was kind of all based around Xcode build. There was other fringe ones, but really like the industry in general in the open source community was doing CocoaPods or Carthage or like any of these other things. And the gist was that people were using XConfigs. Everything was in these PBX projects and you kind of had to like face it and do whatever it did. It was closed source. You couldn't extend it. And you had this like Ruby like project generator built around it. And so that's kind of how people organized all their software back in their day. And they just kind of like let Xcode do with whatever they did. And that works pretty great if you were just using it as like dependency manager and it's just pulling external dependencies. There's not many apps. But when you wanted to like go beyond that, and do stuff like, oh, we've got to like incrementally generate new code, or we've got all these apps that we want to like dynamically configure, or we have like different linking semantics, or we have different compilers, or we have different ways to like run these tools. It kind of broke down because it wasn't really possible to add all that into Xcode at the time. Really, you were up against whatever Xcode was doing. Not that it's a fantastic tool. I feel like it's a great IDE, but as far as like the build system, you were kind of just stuck in whatever they had. And so going to Bazel was like, I feel like back at that point, you basically had all these apps and all these configs that were stuck in CocoaPods. And Bazel was a way to take the build process and organization of the programs into an open source tool and ecosystem that was already like building the Google monorepo. Yeah, I think that's like pretty much a big motivation at that point in history was going to an open source tool and having the ability to describe all of your components inside of build files that the build system used as a source of truth. And you could actually fork the build system, or you could write your own rules in a way that was totally decoupled from the build system. Yeah. It was like, I would say like a revolution that the industry saw when Bazel was open sourced.
Yeah, absolutely. And were there any other bottlenecks or issues with like productivity or CI times or anything like that that were all sort of driving this? I assume that's probably the case.
Yeah, I mean, like, okay, so basically, yeah, like productivity and CI times. It was a huge problem in the industry, and really anyone that used CocoaPods was kind of beholden to the way that Xcode was compiling their source code. And that meant like as far as like how Clang is run or like what Clang you're actually running, or it was all kind of like dictated by Xcode. And so you were basically just given whatever you had to deal with from a build system perspective. And that actually implicated a lot of other problems. Like, for example, the program at the time would check like file timestamps. I think it was later updated to check inodes. But effectively on like most people's CI, they would have to do an entire rebuild of the whole app, and there's no incrementality. Same with tests as well. So like you can imagine, like, hey, whatever your build time or test time is, you got to run this thing. You got to run this build from scratch because it's just doing like file timestamps and not really optimized for remote caching.
Right. And then, obviously, as the code base grows and you add like hundreds of engineers to a project, you start to hit other scaling limitations with those tools and the local development situations as well, right?
Yeah. And actually, if you go back to the fundamentals, like the problem of designing a build system that runs fast on one quad-core MacBook is fundamentally different than designing a program that builds a large repo effectively on many computers and uses a remote cache, right? Mm-hmm. The former one doesn't have to do all the correctness verification. So the latter is actually slower for that use case. And the whole industry had been using these tools, which were like optimized to run on a quad-core MacBook without concurrency and without a remote cache. So it was kind of like effectively like if you had a large source build or a large full source build at a time, and there was a lot of changes coming in, you were basically doing clean builds all the time. Like if you did like a big rebase with derived data, it would effectively like blow out the whole build. And every time you rebase with Xcode, you would have to clean from scratch. It was pretty bad from a like productivity perspective, I would say. And the other thing is that like adding other tools to like run incrementally or as part of the build wasn't as like reasonable or possible to do because the build system itself wasn't very good at being incremental or having correct caching validation semantics. And that kind of goes back to the other topic of like designing a program to work for a large repo is different than a small one, where like this other program, Bazel, it has to know what all the inputs and outputs are. And everything in Bazel is correct and reproducible. So you can guarantee that it's cacheable, basically.
Right. Yeah. Yeah. It's an interesting sort of paradigm, but yeah, it's the hermeticity and explicitness of the build is actually what enables the downstream performance wins. Because without those guarantees of correctness, you wouldn't actually be able to have cache hits that you would feel good about.
Yeah, exactly. Like you actually can't have caching at all unless it's correct. But that's the fundamental problem of things that aren't correct is that they do have caching, but it's problematic. And so in practice, you can't actually use the caching. So it's kind of like, well, we actually need to have SHA-256s. We actually have to know the inputs and outputs in order to not have to remove derived data every time we rebase, because that's like the gist of it. You can't really have like a cache unless you have like a fully correct one because it won't work in practice.
Yeah, there's plenty of heroic efforts to build incremental compilers in various languages. And there are some really complex and non-deterministic tools that a lot of people have serious issues with. So yeah, it's a tough space to work in without taking a different philosophical approach like Bazel does.
Yeah. And honestly, I think you have to kind of look at the problem and say, like, look, like this idea of how to build apps in a small repo with a few developers is actually great. And like the vertical integration of Xcode with all these tools is phenomenal. Everything works amazingly. If you have a small app and a small team, you don't really care about having to like blow away derived data if your build only like 5 minutes long, end to end, right? But when you go to the other situation where like, hey, we've got like several millions and millions of lines of code and we can't actually rebuild these every time we rebase or like make a big change. It's the latter approach of doing a SHA-256, having all the inputs hermetically specified is like a way better approach because you don't have to do clean builds all the time.
Yeah, absolutely. Cool. So obviously the motivation is there. I'm curious if you compared, before jumping into Bazel, did you compare Bazel to Buck, which was obviously, especially maybe back then, it had been open source a little bit longer, also had some decent support from the mobile community. Is that something you took a look at?
So yeah, I would say like back at that point, I was vaguely familiar with Buck, but as far as like the feature set and overall status of Bazel, it was definitely like had more abilities at the time. Aspects and Starlark and rules were the main thing that kind of drew a lot of people to Bazel, right? These things didn't exist inside of Buck at the time, as far as I know. And from an architecture perspective, having the core execution system decoupled from the business logic of how to build an iPhone application or how to run an iPhone test was just like, this is probably the best abstraction that we can have in general, like decoupling these two, because if they're not decoupled, you're kind of back in that situation where like we've got to like now fork the build system or patch it. And it's similar to the vertical integration thing where everything runs in this one monolithic repo.
Right. Yep. Absolutely. Yeah. With Buck, if the out of the box stuff worked for you, then great. But yeah, the extensibility story was definitely not so strong. I think it's more like you could do basically macros. Was pretty much all you could do.
Yeah, in Bazel, if you wanted to run like custom compilers or do other actions, like Bazel actually had a story about what to do, even if it wasn't fully fleshed out at the time. In the beginning, like aspects weren't like fully fleshed out. There wasn't providers, but there was actually a story behind all this stuff, and it was there. So, I mean, it was like a clear win. And from my perspective at the time, it had a lot more features that enabled doing different kinds of things without forking it.
Yeah, absolutely, which is awesome. Yeah, so how did it go during the evaluation? Did you pick like maybe a subset of the app to sort of dip your toe in, or like what did that process look like? How did you like figure out how to define like success criteria and evaluate the tool initially?
I would say if you look at an app, first of all, you can say, oh, we're going to try to convert this thing to Bazel in general, and just say, oh, like it's converted to Bazel, it works. I know there's actually a conference talk about this at one point, and yeah, you could build a subset of an app with Bazel and then like put the outputs inside of derived data for Xcode to pick them up. So instead of having to migrate the whole app at once, that's like one way you could do it. And I think it makes it a lot simpler. And then shipping to users with the Bazel build is the next one end to end. So if you can like do an incremental thing where you start moving over dependencies, that's like a good way to deal with it. And the other problem is that when you start adding in dependencies that have third-party dependencies is where you get into a lot of the other problems, which we can talk about, on like CocoaPods and whatnot.
Right. I imagine that pretty early on in adopting Bazel, you ran like smack directly into that problem. Yeah. And that actually spurred the creation of some additional tools that you found yourself in the position to write because you were really the first one outside of Google to really approach this in the iOS community. And if we look at other parts of Bazel, of course, we've seen other tools pop up to handle external dependencies that are completely separate from what Google might be doing internally because they just vendor everything, right? So it's sort of well known, I think, in the Bazel community that when it comes to external dependencies, the stuff that we're all using is very different than what Google would be doing internally. And so you were the one that had to sort of sort that out the first time in the iOS community by and large. And so, yeah, let me just talk a little bit about that. So you had to deal with these CocoaPods that were, essentially code coming from outside, right?
Yeah. Absolutely. And like, just to like back up one or two steps,
sure.
The apps, like when you would like take an open source app, for example, and try to build it with Bazel, these apps are structured very differently than like what Bazel is able to compile. So the iOS developers have this like include semantic, which is basically library name / header file. That actually wasn't even possible to do in Bazel. So like if you wanted to build an open source app inside of Bazel, you had to totally reorganize the way that you dealt with header files and the way that you dealt with modules. And like that was another thing that was pretty different about Bazel at the time, is that there was like no support to like do any of this stuff. So that actually holds true to an extent today in some capacity, but we can talk more about that. But basically, we need to have rules that could compile open source apps in Bazel. I wouldn't say open source apps, but like apps that are using like the open source ecosystem really. And that was like the big thing for Bazel at the time was you could either like compile all of your dependencies as a framework inside of something like Carthage or CocoaPods and then pull them into the Bazel build, or you could build them from source with Bazel. And I think the latter is like what a lot of people wanted to have happen and what a lot of people landed on, because all the Baroque and complex infrastructure that you need and CI jobs and overhead to actually deal with these dependencies outside of Bazel was just too much. So if you look at CocoaPods, it's kind of a package specification that you really don't need to use Xcode or CocoaPods to leverage these package specifications. So at the time, that was kind of what I was thinking. You could effectively take the entire ecosystem of open source iOS code and take the package specification that already exists and pull it into new build systems. These are two like pretty separate things, like the build system that, or the CocoaPods Ruby thing that interprets the package specifications. The build system, if you just kind of like detangle all those, you can actually integrate the whole open source ecosystem into Bazel. And that's what we had to do like early on to like get Bazel build and get all this stuff in.
Yeah, it's great. Yeah, you're right. There's definitely a different problem there. So there's dealing with building the third-party dependencies. But yeah, you're right that I think, yeah, the other thing that you faced early on was that Bazel was really designed to build stuff in a very specific way, specific to, I guess, what we call like a Google 3 paradigm of how they built their iOS stuff internally. And
Yeah.
you're right that absolutely does not map onto what the rest of us might be doing that are following like the more common patterns you would see in the open source and would be almost prescribed by like the examples of CocoaPod's usage or something like that, right? And so, yeah, that was the first gap to build a bridge over. So, yeah, maybe we can drill a little bit into that because I know you did some work probably on, like the module system there. And what did that work look like, at least in the early days?
I feel like the most complicated part was trying to take these CocoaPods-based apps and compile them with Bazel. That included the first-party code and the actual third-party code because it was all structured. Like if you looked at trying to build something that used CocoaPods on the internet with Bazel, it just didn't work. So there was like 3 or 4 things that you needed to tackle from a build system perspective. Package management is a whole nother can of worms we can talk about as well. But from like a compilation perspective, Xcode used this data structure called a header map in order to import these headers. And header map is like a preprocessor level kind of thing that allows the compiler to look up headers in arbitrary locations specified by a hash table, which maps in kind of like a name to a file location, so to say. I guess that's a simple way to put it. And so at the time, there was no way to do header maps in Bazel itself. So this was like basically a point where I had to either look at, like maybe we can add this as a Bazel rule. Maybe we can add it to Bazel itself. I actually was like looking at doing it both ways. There was PR to Bazel to add this data structure into it, but I think it added too much complexity and wasn't aligned with the direction that people wanted to go at Bazel. So implementing that header map structure inside of a Starlark rule is what's in podToBUILD. That thing can basically take your header files and assign them into a namespace that will work with whatever convention you were using CocoaPods. This was like before providers. It was super hacky. It actually propagates a header map, which is transitively merged.
Yeah.
So that, and then let's see, Clang modules themselves are like pretty an interesting state in general. Does that make sense for like the header side of this?
Yeah, absolutely. And I think it's important that the end result is that you can preserve the developer experience that most of us coming from like the open source ecosystem would be used to, right? Where we can use the imports without too much hassle, right?
Exactly. Yeah. And like that was the idea. It was originally implemented as symlinks, the whole mapping. There was actually symlinks that are created in podToBUILD. And I think it's actually, unless you set enable header map, it's true. I think it does that. But basically, like, the header maps enable the compilation to work. Module maps, not super interesting, but it's a similar problem where like these idioms and ways that the developers use compilers under Xcode and CocoaPod just didn't work. We had to like figure out a way to like map these idioms into Bazel. After that was done, everything just kind of works, right? Actually, like looking at CocoaPods in general, CocoaPods doesn't have the same kind of insights that Bazel can have. So the way that Bazel can actually treat some of these data structures and something like a header map can actually work way differently. Like, so it can actually run a lot faster.
Yeah, very cool. And so, yeah, I want to make sure we dive a little bit deeper into like the package management side because I think there's a lot of interesting stuff going on there as well. So so obviously pod spec, we were talking about package specification in a Ruby file, right? So yeah, maybe talk us through a bit of your work in that area.
The pod spec specification was one of the coolest things that I had ever been introduced to when it came out, right? There was this massive effort across the industry to put open source code on GitHub and put it in a common format for the whole industry to share code on, which was just like one of the coolest things ever. And I feel like this tool CocoaPods actually brought together a bunch of developers in the community. It was an amazing time to be part of the community, and like they had really like banded together with this package system totally from the open source. And there's effectively 2 sides of it. The first one was the package specification, and then there was a tool that read in all those package specifications. There's no other tool that could interpret the package specifications at the time. And so effectively, you have all of your source files, all of your dependencies, and all of your compiler options in this package specification, which is just unbelievable. Like, not many other ecosystems have even something like this. And so I was like, well, we can take these pod specs and then put them into Bazel if we already have like all the build system side of this organized and sorted out. So that's kind of what podToBUILD is, right? It looks at the pod specs and then it puts those into Bazel. But there's a lot of differences between how podToBUILD works and how CocoaPods works in general. But the main one is that podToBUILD looks at the package specification and it has convention that it uses to map to other CocoaPods. So each dependency in the dependency graph in CocoaPods is treated as an atomic unit inside of Bazel. So there's no lock file. There's no like analysis of a global dependency graph, which is actually problematic as you scale and add thousands and thousands of dependencies in CocoaPods. It has to like analyze all these state. And so with Bazel, we basically treated everything as an atomic piece and everything kind of bootstraps together with a convention in the labeling. And it's a very simple system and very easy to add. There's some pretty Baroque graph algorithms and like different interpretations of Ruby inside of Bazel and CocoaPods, and podToBUILD.
And imagine that I run into the diamond dependency problem somehow, in my CocoaPods graph. So CocoaPods, I guess we get around this with actually doing dependency resolution using a lock file, right? And I don't know what their resolution algorithm is, but probably one of the more common ones out there, like was LCES or whatever the one is. I'm forgetting the name of it. But so in your case, you're generating a unique. Say I have two different versions of the same dependency. What happens? Are we generating two different external repos, or what does that look like?
Yeah, CocoaPods has a resolver that will kind of pick whatever dependency it picks. And it's pretty abstracted away from like a packaging perspective. Bazel doesn't really do that. You have to specify all the transitive dependencies inside of a workspace file. You can literally pick what checksum you want for all of your dependencies. You don't have to leave it up to an algorithm. This makes it possible that you don't have to have a lock file either, and you don't have to worry about dependencies being updated from underneath you.
Right. Gotcha. Okay.
You get one dependency in one SHA-256 of it.
Cool. Yeah, that's great. And so with that implemented, you're ready to start building your app, I guess, right? You figured out how to preserve the import structure and at the same time, like just basically make anything that the CocoaPods source, actually do, like make that all work. And then you've actually implemented your own dependency resolution essentially, and you're pulling down stuff from CocoaPods, you're generating Bazel artifacts from it. Now you're moving into actually building the apps and building your first party libraries. Like, what does that look like? I guess what's the next sort of host of issues that you run into at this point?
I guess it depends on what year you look at, but yeah, it's pretty funny to think that you would have to like either compile the CocoaPods from source and then get all these things working in the build system in order to even compile your app. It's pretty funny that it was that complicated back in the day.
In your specific case, I'm just trying to run through the journey. Yeah. Like the good news is for people listening getting disheartened, the good news is a lot of this has been solved, and we'll definitely talk about what that looks like today. But just in terms of Jerry's hero's journey through making this all work, I'm just trying to get a sense of, like what came next, if you can remember that far back.
I mean, the Swift rules at the time didn't even exist. So it was right. You couldn't even compile Swift source code with Bazel at the time. Like it wasn't a thing. So yeah, figuring out like what the path for that was going to be, and then hooking up how podToBUILD compiles things into your app was what you had to do basically. Yeah, have some like macros to like compile the apps with podToBUILD, and then pretty much that's the gist of it, right? Because all those rules about how to deal with header maps are open source and were in podToBUILD at the time. Mm-hmm. So if you were like building a application that depended on CocoaPods and on the ecosystem, you could easily take in the rules that were in CocoaPods and then basically run those on your own build. That was really how a lot of people were building apps at the time. They're kind of like using podToBUILD to manage the dependencies, and then the header map rules were in podToBUILD, so you could just run those. And I think someone even made like a very similar header map rule to like what podToBUILD did in another repo as well.
Right. Yeah, exactly. You mentioned obviously this was before Rule Swift even existed. So at this point in time, did you have any Swift code, or were you just building pure Objective-C?
podToBUILD was pure Swift. It was actually compiled with Xcode because there was no way to compile with Bazel. So it's an Xcode based build. In the first couple commits of it, it was built with Xcode. The Swift rules eventually went into Rules Apple, and so you could compile Swift with Rules Apple at one point, and then it was factored out into its own thing. And at that point, then people were building Swift with Bazel, which was really great. So I feel like after you got like Objective-C to work, getting like Swift to work was another non-trivial feat in general. Also at the time, I think they were on maybe like Swift 2 or something like that, barely even like Swift 2. So it wasn't like the language itself was pretty new still. And I think people weren't sure how to adapt the compilation model into Bazel at the time. But I mean, it's a very different compilation model than like Clang, for example.
Oh, yeah, absolutely. And so during your initial adoption of Bazel for the flagship app you were working on at the time, were you struck by the lack of Swift support, or was this at a time where that app just didn't have much Swift to be concerned with?
It depended on what you were working on as far as like an app. But yeah, like Swift support worked in Bazel, so you didn't really have to worry about it at like some point. I forget when they actually added that to Rules Apple. At that point, you could just call like Rules Apple. That would like hook it all up for you.
Yeah, gotcha. Yeah, well, so I guess the next issue that can be met today in this regard would be folks that are currently using Objective-C and Swift, even in a modern app, which of course a lot of people are doing this. There's this idea of a mixed source module, which is a term that strikes fear into the hearts of Bazel users even still, I think. So yeah, maybe let's talk a little bit about some of the issues there under Bazel, what you've done to work through some of that stuff.
Yeah, absolutely. So the mixed module is pretty cool. In general, they have the ability to compile Swift code that imports Objective-C code. And when this bridge is invoked, it works pretty nicely for the default SDKs and frameworks, which all have Objective-C header files and module maps in our modular. Basically, the issue is that like people had the Swift code that was kind of like importing Objective-C code from either an external module or it was baked into the module. It's called import underlying module in Swift, which kind of like loads in the module implicitly into the namespace that you're using. So you can like access the code as if it was part of the Swift module. And this wasn't actually like supported in Bazel at all. And podToBUILD actually had an implementation of this pretty early on in order to get a lot of the open source SDKs compiling with it. And because basically the way this bridge works is the Swift compiler has to run Clang inside of it. The Clang compiler is baked into the Swift compiler, and it runs the Clang compiler to collect all the headers and create the modules from Clang, and then that's how the language bridge kind of works, right? So all the logic that was already done for the Objective-C with header map and all that other stuff just had to be added into Swift, and then we call the module maps. And really, that was kind of like the fundamental pieces to get mixed modules working in podToBUILD. And then I think the last one was like extending the module interface for Swift. And so that was added pretty like shortly after. And we had mixed modules like totally up and running in Swift because there's a lot of, I would say like maybe on Swift 3 or 4, we saw a lot of open source dependencies in the ecosystem transition to using Swift. So that was finally expected in podToBUILD to work.
Yeah, it's sort of non-negotiable when you're dealing with the open source code. And yeah, so this is an issue definitely that a lot of people still struggle with today. And I think one important thing to stress now, and definitely I'll have someone on that can talk in more detail about it, but the mixed module stuff is slow, like much slower to compile, even with the vanilla tool chains. And so there's a performance implication when you're mixing your modules like that. And so even outside of Bazel, there's a problem there that you need to be aware of if you're building at scale, because that can be, I guess, a big bottleneck in build, even outside of the context of these advanced build tools, right? And then under Bazel, it seems like obviously this issue is only exacerbated or at a minimum just not alleviated at all. And so you're going to slow yourself way down mixing the modules. So it sounds like you have definitely some thoughts on that.
Yeah, I mean, it's definitely interesting. The overall importing of those modules is definitely problematic depending on how you structure it, right? You can look at it in a couple ways of like, hey, this is a build system problem or it's a compiler problem. And I feel like people have a combination of both of these problems where it's like, yeah, the compiler and the build system need to kind of be aligned in order for all this stuff to work. The other thing is because all this source code in the open source community was implicitly compiled as a mixed module in CocoaPods. CocoaPods basically compiles everything as a mixed module by default. So you had to do this in podToBUILD, compile them as a mixed module because that's how they're compiled in CocoaPods, right? So there's like the problem that you have to fix your source code to not work like this. You have to refactor your source code a little bit and then make it import external modules. Yeah, it's a pretty interesting scenario. And I feel like in general, the module system, it needs some work to actually work correctly inside of Bazel and remote execution. And there's actually a lot of work to be done here around like client modules and mixed modules and like integrating this all into the Swift compiler. It's definitely up for grabs. So I'm excited about that.
Cool. So at this point in your journey, you've worked through all of these roadblocks so far. I guess the remaining issue that seems obvious to me, at least, would be you've got this stuff to a point where it's working in the CLI, we'll say. That's an amazing feat. You patched all these module systems. You've got all this stuff working. The open source model sort of brought into Bazel. That already is like a huge accomplishment. But then you've got this last mile problem of it works on the CLI maybe, but in Xcode, not so much, right? So that I think probably led you to create another tool that a lot of listeners will also be familiar with. So maybe talk us through where you were at during your adoption and sort of what that looked like. I guess what was your thought process as you realized that there's just no way that this is going to plug right in and just work in Xcode?
My original thought was, hey, don't use it. Let's just use Vim. I've got a couple Vim plugins that run source on GitHub. You can just use them.
There you go.
Yeah, no, that's too funny. I feel like the gold standard of iOS development is this phenomenal IDE that everyone uses called Xcode. And it's really a marvel of engineering with the auto completion and how smooth the UI flows together, this code searching. And it's just unbelievable the quality of IDE that we have. So I can definitely empathize with people who want to keep on using that. But there's a lot of assumptions in the XML generator, that XML format and that IDE, where basically the IDE is kind of like assuming that it's a build system in order for it to work. So when you gut out the build system, you're kind of at an interesting state. And Google at the time had a project called Tulsi, which worked pretty well for the default way that you were building an iPhone app with Bazel. If you follow the instructions, they created a generator which was effectively instrumental to get this thing up and running, but it didn't work exactly how people had the IDE running in CocoaPods. If that makes sense. Tulsi was amazing. The fact that this thing could generate an Xcode project from Bazel was kind of the basis of how to integrate this thing into Bazel. But at the time, even if you use Tulsi and use Bazel, you'd get faster builds, but stuff like the progress bar or there's maybe 5 other things that didn't work if you use Tulsi. So yeah, that was a hard sell because some developers out there might really want to use these features and some other developers might not really care so much. They just want to compile fast and deliver impact or features. But yeah, some of the other developers might actually need all the features that it has. So that was kind of the time where people decided hey, what if we could take Bazel and what Tulsi was doing and make an Xcode project that looked exactly like CocoaPods. So effectively, that's what XCHammer does. It kind of looks at your build graph, and the first version of it made an Xcode project that was like CocoaPods. It didn't actually compile with Bazel. So all the features would work in the IDE as they did with CocoaPods, where really any of the UI features worked identically because it was just treating Xcode as kind of like a compiler and plugging in all the right build settings to make it have the same errors as Bazel.
And so when you hit the build button, at least in the earlier days, what was happening under the hood?
So the build button effectively just ran Clang and Swift and Xcode, just like how they would work. And inside of that program, it makes the build work just like Bazel. So as far as from an error perspective or really any other perspective, it works the same as the Bazel build does. You have everything set up correctly in it. So yeah, that was the first version. And then finally, at some point in the future, that program gained the ability to just swap out the build system to Bazel. So the project was already amazing. It was pristine. Everything was phenomenal in the Xcode project. It looked just like CocoaPods. The last thing was to just make XCHammer build with Bazel. And then that was added several years ago at this point. But there's one attribute you can set. You can toggle between Xcode or Bazel. And it will give you either Xcode or Bazel builds and look exactly the same. There's some other changes we can talk more about those, but yeah, that's really the gist of the program.
Yeah. And so at that point, you're getting the best of both worlds. You've got, working IDE experience. You've got external dependencies, presumably with some autocomplete going on. And then you get the benefit of sharing that remote cache and a fast incremental build with Bazel, all with one tool. And yeah, I think it's important to touch on. Tulsi is a great tool. It's just that again, it sort of assumes you're going the Google 3 sort of setup route, and all of your previous work at that point was basically breaking all of that to support CocoaPods, right? So yeah, it's kind of had to jump back in. And if I'm not mistaken, at least at a certain point, you were reusing some of the aspects that were kind of shipped with Tulsi, correct?
Yeah, and so honestly, if you look at the amount of code and complexity that it takes to run Bazel from Xcode, it's not trivial. And Tulsi already does this, and it was maintained by Google at the time. Mm-hmm. And so I was like, look at this Tulsi thing is phenomenal. It just needs a different Xcode front end to it, different project generation front end to make the project look like CocoaPods. And that's what it does today. The build system is kind of based on Tulsi, where Tulsi actually runs Bazel and then reads the BP to do various things. Mm-hmm. And the aspects, we're literally just using Tulsi's aspects to extract the information about the rules. Mm-hmm. So all of that code was maintained in Tulsi, and it still is today. Tulsi has the basis of it. So yeah, I mean, it's pretty phenomenal. That project is only a few thousand lines of code end to end.
Mm-hmm. Yeah, it's great to be able to reuse that awesome code from Tulsi. Yeah, cool. So all right, so at this point, this is definitely a great, I think, overview of what adopting Bazel in the earliest days would have looked like, where there's just a lot of gaps that you had to fill coming from the open source sort of ecosystem. And yeah, I mean, I think definitely for us, at Flare and some of our previous companies, we definitely made use of these tools in the early days because there really wasn't much else out there in terms of getting started with Bazel in the sense, if you were to compare it to Buck, Buck, you could at least get up and running. Again, there's obviously limitations there, but with Buck, you could build your iOS app at least. And then, with Bazel, it's quite a bit harder, but that's where everyone wanted to get to because of the extensibility and multi-language support and all that stuff. So yeah, and then of course remote builds, which is not a feature that Buck provides, right? So we were big users in the early days, big fans, and it was awesome just to have anything in the open source to really take a look at what's going on under the hood there. So yeah, it's a great addition to the ecosystem. I think definitely a lot of the work that we've all done so far if we didn't use it directly, definitely informed by your early contributions. So yeah, thanks a lot, man, on that front.
I'm glad people got a use out of it. I didn't really know if anyone would have value in it, but if you look at other open source projects, Bazel itself it basically started a revolution of iOS build tooling, and same with Tulsi. So I think having these tools out in the open is very important, and I'm so glad that you were able to take use of it. I think we have other things now. Now there's a lot of other different amazing things in the ecosystem as well too.
Yeah, absolutely. So I definitely want to transition to that. So 7 years ago, when one was adopting Bazel, very different set of problems than one would have today, luckily. So we don't all have to be Jerry to build our apps with Bazel, luckily. So yeah, so nowadays there's a plethora of options out there for folks, maybe almost too many, right? So the not official, but the Google and community maintained Bazel rule sets under the Bazel Build organization. So today we have great support for Swift. Rules Apple continues to be great. And, there's still a couple of issues there. The first is the mixed source modules. There's not a solution today. So if you have mixed source code, your only option is to refactor it or to take a look at some of the other community tools that we'll talk about. So that's sort of the one issue. And then the other is, I would say, you're still going to have some issue potentially with IDE support once you start going down that route, right? So that's sort of the other sort of issue that everyone will often run into, is that using the out-of-the-box tooling, Tulsi, there's still probably a little bit of patching you need to do because you're not going to be building your app, which is probably still using CocoaPods. You're probably not building that in the same way that Google is, right? So those are still sort of some issues that people are going to need to have some solutions for. But the good news is here that in addition to the older tools that you worked on many years ago at this point, there's also a current effort that you're leading at your current position. And this is something I think that's awesome and that a lot of folks in the community have already gotten great use out of. And this is sort of, for someone adopting Bazel today, they're gonna say, okay, I have this great stuff that's part of the core support that Bazel provides. I've got these gaps. How do I fill those? And then inevitably they're going to look at Rules iOS, which I think we should definitely dive into. So that's a great option for patching up some of these last holes. You can also roll your own solution to these problems, as many organizations continue to do. Whether or not that's a good choice is, it's up to them, not to me. But yeah, so as a new adopter of Bazel for iOS today, I think inevitably someone in the community will point you to rules iOS. Definitely I will. And so at that point, maybe tell us a little bit about, what's the elevator pitch for why someone adopting Bazel today might take a look at the rule set you're currently working on.
It's going to work. Everything just works. Like literally, you can just build your whole app with rules iOS and it works. We also have an Xcode project rule that is just going to work. You can literally have everything working with just using rules iOS. And we actually have a flag that you can turn off mixed modules if you fix those in your source code.
Yeah.
It's that easy.
Awesome. Just works. That's great. So let's dive in a little bit. So some of the things, and actually I think there's a lot to unpack here. But so I guess first of all, how does the project generation piece and the potential support for third-party modules, how does that relate to your earlier work? So we got an implementation of rules iOS and then some earlier work, from many years back. Or what are the big differences there and changes maybe? I imagine you're thinking along these lines. It's probably evolved over time as well. So maybe run us through some of that.
Absolutely, yeah. So rules iOS, it doesn't have a external dependency management system built into it. People that use rules iOS, they either use a program to generate and install CocoaPods with CocoaPods itself, and then make a build file that uses rules iOS on the output of CocoaPods effectively. People that use CocoaPods with rules iOS use it like that. Everything literally just works. It's that easy. The crazy atomic unit treatment of CocoaPods isn't happening that way, but everything will literally just work for you. You just have to run pod install. And then that program, CocoaPods Bazel, will literally do everything for you. It just works. On the Xcode project generation side, there's a rules iOS specific generator that literally works amazing. We basically have every test case and possible permutation inside of rules iOS on GitHub supported, and we have a test case for it. So anything you can throw at it with rules iOS pretty much should just work if you're using rules iOS. It works very well because it's a very contained kind of problem, and it's a very easy way to build an iPhone app, and it is identical to how people do it with CocoaPods, which makes it so easy.
Right. Okay, gotcha. And so what if I decide that I want to build my CocoaPods from source as part of my Bazel build with rules iOS? What does that story look like?
Totally just works. You basically will install CocoaPods-Bazel from Bazel build/rules iOS. You're going to run pod install, and then that thing will basically set up the external dependencies to compile based on how CocoaPods transform source code. And that's one of the things that CocoaPods does. And then it's just going to work. It definitely doesn't have a similar paradigm as podToBUILD, but it's a lot simpler to do it like that.
Yeah. And is there any inkling that you might look into a similar approach in the future? Because obviously it is, like you said, it's a sort of a different paradigm altogether. And obviously some of that might be by design, right? There's a lot of complexity and code to maintain and podToBUILD, right? So is there any sense that getting back into some methodology like that allows you to really manage your dependencies all directly with Bazel and maybe get a little bit more caching, incrementality, remote execution out of it? Is that something that you've thought at all about? Because I would imagine that if we're relying on CocoaPods, we're also probably not able to effectively build remotely much of the external dependencies, which is probably a decent chunk of time on big apps, right?
So the way that CocoaPods Bazel works is it actually will generate source code, input it in pods, and then install a build file. So it actually works just like any other source in your tree. And with the remote execution V2 APIs where everything's described, theoretically, once you've ran pod install, it should compile everything remotely. The problem is that from a scaling perspective, using the global state in CocoaPods and having that pod install time and expecting everything to run through that it adds a bottleneck in some cases. So on rules iOS, there's an issue to add podToBUILD to it, which can do a couple things, mainly treat the dependencies as atomic units and basically be very specific about building complicated dependencies identical to how they built in CocoaPods land. So it's kind of from the making the build work just like it did in Xcode and treating the dependencies as an atomic unit. And moving away from CocoaPods in general is what podToBUILD is really good at. But people do it like either way with Rules iOS. They'll have like some program that like downloads dependencies, or they just use CocoaPod's Bazel. And
Gotcha.
I think that works, especially if you have like a few dependencies in a smaller app.
Yeah. So, okay, it's potentially on the roadmap as something you might take a look at in the future then. Gotcha.
There's a GitHub issue for podToBUILD in Rules iOS.
Yeah.
But I guess we'll see like if someone in the community jumps on it.
Gotcha. Cool. On the project generation side, what are the key differences going on there versus your prior work? I don't know if we drilled into that too much.
So there's actually a PR for that too. There's actually a PR to add XCHammer to Rules iOS. Mainly, that PR will work under the hood. So whether it uses the current implementation or uses XCHammer, it will kind of be opaque and everything will, again, just kind of like chug away. However, the other things that this will enable is building without Bazel to get those last IDE features if those are really important. And finally, XCHammer has like integration with the progress bar. So that's like another thing that people want to get. Yeah, I mean, it's pretty exciting. So there's a PR up for that. It will be pretty much like a feature and like an opaque kind of transition, and all the test cases that we have on the CI should effectively like just work with XCHammer.
Oh, that's awesome. Yeah, very cool.
Yeah, I'm really stoked about it because I feel like there's a lot of architectural problems to solve here. We have like all these different kinds of rules that are very different. Like Rules iOS has some pretty different linking semantics and different ways of even processing like ARM64 dependencies to make them just work. To get Rules iOS working just like Xcode, there's a lot of different stuff in there that I had to do to fix some of these things. And those work a lot differently than the other rules. So it's an interesting architecture problem. You've got all these different kind of rules and you've got to make them all work with Xcode. So how do you actually do that? And I think that's an interesting problem to address. The problem of generating an Xcode project is already solved. So we just got to hook all the rules up to it and then have test cases for it. And then that's really, I think, going to be the end of it.
Yeah, it's great. I love it. And so, yeah, so you touched on a little bit on the ARM64 stuff, which we've covered on a different episode that people can definitely go take a look at for an in-depth conversation on this. But just at a super high level, assuming I've got an app today that I'm building, with some maybe vanilla build tools and probably inevitably going to be hitting issues with some of my vendored pods that maybe they haven't released ARM64 updates. And so I'm running the IDE with Rosetta or something like that. So this is something you've done a recent blog post about it, but what is a reasonable expectation for if I adopt Rules iOS? How is this going to change?
It's just going to work. I mean, it's going to take the XC frameworks and it's going to take the frameworks that you have, and it just kind of works. Like it's a pretty easy system. And like at a higher level, if you look at some of the test cases on Rules iOS, it basically exemplifies every permutation that you need to do for Bazel and just takes it and that's it. There is some features that you have to enable in the Bazel RC for it to just do this. But if you have an external dependency within XC framework, all you have to do is drop a build file in there for Rules iOS. And that's really it. This thing just kind of chugs away and compiles all the code.
Yeah. And not only that, it's not only just going to work, it might even work better than before because, I might be able to even take a build of a binary built for a different architecture from device architecture and actually make it work on my ARM 64 MacBook, right? Is that true? Or is that overselling?
Oh, yeah, it works. Yeah, like it literally is going to take the ARM. I know I keep saying it just works, but it really is that easy. Like there's like even a test case for this on Rules iOS where it compiles all these rules with device dependencies. And it actually runs up to 4 times faster than CocoaPods in some cases because of all the like build engineering that we did in Rules iOS. So it's kind of like if you have an app that is running on CocoaPods and you literally just take that thing and build it with Rules iOS, the build times are fundamentally faster. You have to enable some features and there's definitely some caveats with some of those optimizations, but at the end of the day, it kind of just will work and like do everything correctly. I think this is very important for the Bazel ecosystem to have a tool like this that is just literally taking whatever Xcode did and then running that in Bazel and doing it way faster.
And then, of course, we can add remote cache and execution on top of that. And we can go from 4 times faster to 40 times faster. That in the optimistic, mostly cached case, of course.
Yeah, you're right. That is probably around like the games that you'll see with it, probably around like 40x. You have like a CDN hooked up to it. But yeah, the rules are like fully hermetic. Someone added from the community that like awesome feature to turn off the mixed modules. And I think it's pretty cool. So I'm pretty happy with the state of it. Just the last couple polishing bits, and it's going to be awesome.
That's great. And yeah, so you touched a little bit on the CDN. So this is something I know that you've also been taking a look at for trying to really speed up the builds even further. So I'm curious what we can drill into there. I mean, obviously, with all the caveats that can't talk too much in detail or any other implications. But yeah, so tell me a little bit about the route you've gone down for implementing like a CDN in front of your cache for Bazel.
Cool. Yeah. Well, basically, everyone back in the day used to be at an office. Like people used to commute in their cars to an office, and that office either had like a fast connection or a cache in it. Like you were like in like a major city at some office, you could effectively go there with your coworkers and have a Bazel remote cache. I think that's like what a lot of folks did back in the day. They had like some caches set up, which was network adjacent, and maybe they had like a fast link to a data center, or like they even had a data center closer to where their office was. I don't know. But effectively, when like 2020 came around and people started moving from the office to home, suddenly like Bazel remote caches weren't as effective as they used to be when you had network adjacent, low latency access to a fast cache, right? And so I was kind of like, well, Bazel remote caching is as effective as you make it. And same with remote execution, right? So that's when I kind of got the idea that like, hey, on like mobile and other computing spaces, people made a very effective way to transmit material to mobile devices or devices all over the world. And it's actually a solved problem. And so at that point, I was kind of like, I need to make Bazel remote caching work in this like work from home environment. And I was kind of like, well, let's bolt a CDN onto it. And I mean, that's really, it actually fixed the problem and made Bazel remote caching viable by leveraging remote caching and edge computing. And that's really, that's really the gist of it.
Mm-hmm. Yeah. We don't often talk too much about our products on this podcast, but yeah, we, of course, are in this space as a similar issue, and we have a lot of metrics also on it. And so to dive a little deeper, so you mentioned latency. That's a big one here. So there's a couple things going on. The first is the gRPC protocol itself is just TCP, unfortunately, or fortunately, depending on how you view the problem. But it's TCP. It's just HTTP 2 under the hood. And then, of course, you might, in your implementation, you might be using HTTP even. So we'll talk a little bit about that too. But if you're using gRPC, the gRPC protocol itself is impacted a bit by latency. And there was an old issue with window sizing that really made the problem extreme for users of gRPC outside of the data center. And that has since been addressed. And I would say it's probably 90% solved. But that said, if you have a high latency, I would say the gRPC throughput overall still can suffer. And so that's sort of one insight. And then the other is that Bazel itself, the remote execution protocols are a little chatty. And there's been some recent fixes here to kind of cache some of this stuff a little bit more in Bazel and do a little less back and forth. But the reality is that it's going to make, during the course of a build, millions of calls essentially to the back ends to check things and double check things and recheck things. Just outside of the downloads, there's a lot of metadata and a lot of stuff going on, right? And so the net result is that if I have like a 10-minute build and I've got like 100 milliseconds of latency, if I can reduce that latency down, I can reduce that build time down by like the same or more of an order, right? So we would see things like we might have a 10-minute build using a remote cache, and then without the remote cache at all, it might be like 8 minutes. So we're only adding overhead because of the latency here, which is really unfortunate. Doing the work locally is just faster in some cases. That's not what we want. We don't want to slow people down with our product, right? That sucks. Yeah. I think the next really interesting thing was driving that latency down. We really found that we could really increase so definitely avoid the case of ever slowing anything built down, but then also just like getting more performance, right? Because Bazel needs to check the remote cache to see what kind of work it actually needs to do locally. So it does kind of have to block certain tasks and stuff until it gets the answer from the server. And so really, really speeding that up by lowering the latency alone can make a big impact. And so, we would see, cut the latency in half, cut the build time in half easily, right? So we could take a 10-minute build of some, TensorFlow or something and cut that down to like, 2-3 minutes just by reducing the latency. Then we can take that, of course, further, right? Where we can actually speed up the transfer, which is the next thing, right? So it's just like the latency is a big thing, but then speeding up that transfer is also another big thing. And that's where having a CDN, just putting all that data closer, every single packet is just moving faster. You can even get higher throughput and stuff again because of gRPC, like we talked about. So increasing that throughput makes a big impact on the download speeds as well. And so our implementation product's a bit different than yours. And so I'm curious, before we but I don't want to talk too much about our stuff here, but I'm kind of curious, like the CDN you deployed, maybe talk a little bit through, like, is that using HTTP? Is that using gRPC? Like, what does that look like?
So yeah, the one that I currently deploy it's using HTTPS, and there's a CDN that effectively mirrors what the Bazel HTTPS protocol looks like. So if you can do that, like you can, it kind of just works. And they have pop location everywhere. It's a massive CDN. I'm curious to know more about some of the stuff that you guys did on like really like optimizing remote execution and what kind of benefits that you see going over from something like a CDN to like remote execution really get. I don't want to derail the podcast, but I'm
sure. Yeah, no, I think it's a great conversation to have. So I think that there's a couple issues with using HTTP. So the first is Bazel's HTTP implementation uses HTTP 1.1. So this means that you've got the overhead of opening a new TCP connection for every single request. There's some overhead there, of course. Even if you raise the max connections, it'll often just be slower than just using a gRPC interface. We actually have an HTTP adapter to our cache. So like behind the scenes, it's the same thing. HTTP is always slower, and we have gone way overboard in optimizing the HTTP implementation on our end. It's just in the Bazel side, HTTP client, JVM, whatever the issues are, it's just much slower. And again, you were comparing HTTP 1.1 to HTTP 2, which does multiplexing. You don't suffer the overhead of dialing and all that other latency that you're adding with all that kind of stuff. So the net result is that just in a pure like apples to apples comparison, as much as you can do so with the HTTP versus the gRPC implementation, we find that gRPC is just going to be faster.
Yeah.
30, 40% faster, something like that. So that's sort of the first takeaway. And then the next would be the remote execution protocol, right? So if you want to use remote execution, your remote cache needs to be like the same endpoint, right? You can't like use an HTTP remote cache and then a different remote executor. And so this is because the remote cache and execution APIs are the same APIs. And the remote execution of an action is really just a remote cache with one extra call of like, hey, I uploaded all this stuff, so build that for me remotely. And so that's really all it is like an extra execute and some other polling calls, right? So everything else, it uses all the same methods in the protocol for caching and execution. So they are kind of tightly coupled if you use them, right? And so what we want is for the thing that really is speeding up most remote builds is that they're mostly cached. Like there's a great white paper out of Google that I'll apologize ahead of time. I'm going to get the statistics a little bit wrong, but it's something, they have a great graph of like something like 95% of the builds are like over 90% incremental. And so if you make that assumption, then like your remote builds are just 90% cache and then 10%. Again, there's outliers that are going to be maybe building the whole build graph, and that's where the remote execution like speeds things up. But that's sort of the key takeaway is like, even for a pure remote build, you want a fast remote cache. And ideally, like you want to have a CDN serving your remote builds and not just your non-remote builds, right? And so that's sort of our approach, is to use the CDN as sort of an entry point no matter what. So if you're using remote execution, you're still getting those cache hits off of the CDN. And so we implement it over gRPC. Now, what that means is we have to build our own edge nodes. We can't go take advantage, unfortunately, of something like a CloudFront or, plenty of other alternatives out there. Of course, Google has one, and then there's, Akamai is more classic, right? We can't really easily take advantage of just like simple pre-existing infrastructure. And so that's where our implementation would be a little bit different, in that like we've written edge nodes that implement the gRPC protocol at the edge, and they're doing a lot of other things there to sort of further optimize this. And so the net result though is that we can put our edge node in front of any remote execution engine and make it 10 times faster. And we've done this with all of the open source alternatives that are out there. And we know that our customers are fronting other commercial solutions with this, and maybe we stacked the deck in our favor, right? Where we're like, okay, let's like minimize latency, and we've done a few things but yeah, in general, if you have like very unoptimized setup, adding the gRPC CDN in front of it can make like an existing remote build 10 times faster, which is awesome. And we've done again, like a lot of optimization in the edge node, where it does like a hybrid of in-memory caching, even of like the hottest stuff. We don't use syscalls really anywhere in our stack. It's too slow. We try to use swaps as much as we can. So like, basically memory map everything out to disk and stuff, and that's a more optimized path. So yeah, we're pretty happy with the results. There's some other overhead with the gRPC protocol as well, where if you have a few different hops, it's going to be like encoding and decoding a bunch of data. We have custom codecs and stuff to really optimize all that, and a bunch of other little manipulations like that have kind of come over time. It's kind of like with Bazel, we see this theme all over the place, where we're sort of taking like tools that work great at Google scale, on Google infrastructure, on Google Fiber, Google Cloud machines, right? All this stuff works great inside of a Google office. When the rest of us try to adopt it, there's often hurdles that we have to overcome. And so obviously a big theme in your work and in ours is really making Bazel work in a context that's kind of a little different maybe than it was designed for the Google, like the Blaze use case. And so we find that obviously with building iOS apps and the same with making these remote protocols, work effectively. Even gRPC, like making gRPC work effectively outside of the Google data center is like a big optimization problem, right? Like at every level of our stack, we have like pretty significant forks to gRPC. Our C code uses like a custom fork of the gRPC core and stuff. So I mean, we're getting in there.
Nice.
And so yeah, there's a lot of fun stuff to unpack there. But I think by and large, I would definitely be curious. Like, do you have some strategy for executing a remote build and then sort of backfilling the cache, or like how does that look? Like, or are you just using completely like siloed caches for remote builds versus just remotely cached builds?
So it's pretty much just like writing job to the cache. A known good build is effectively like pushed up to the cache. And so when you hit that thing locally, it doesn't have the remote execution bit added onto it just yet. It kind of will just like hit the CDN for an artifact that's known to be good from like a trusted pipeline. And then that thing just like flushes out the artifacts that you need, and so you can hit it locally. And there's definitely like in the actual CDN itself, it can do some pretty heavy optimization and caching policies. So a lot of issues that you would get if you just use this thing against like a vanilla server, just like sitting on AWS, aren't like there, because the CDN edge nodes themselves are like super local to a lot of big cities, or even in like San Francisco, for example. Mm-hmm. And that thing like might be like down the street, for example, and the overhead of like hitting that thing is pretty negligible to the point that it was running pretty fast. I think this is actually like an interesting paradigm. We got Bazel, everyone's like super stoked to use it, but they need to have something like Flare to actually make remote execution work right, or they need to have someone that like goes in and optimizes network latency and deals with all these end-to-end problems and like kind of makes it all fit together in order to work.
Yeah. I
think it's a huge like selling point that you can like just kind of get Bazel, hook a remote cache up to it, and be up and running. And then there's like, we've either like dramatically messed up build times because the implementation is so bad and everyone's working from home.
Yeah.
I feel like the latter, I actually feel like the latter position is pretty much the state of the art. And like, there's actually a GitHub issue on this around like remote caching on Bazel not like being beneficial. But the answer is, in my mind, like, hey, you have to solve the like end-to-end networking problem, and that network has to have a very fast path to the file system. And then that file system has to be sitting on memory or like a fast hard drive. Yeah. I think the funny thing about Bazel is that it's effectively as good as you make it. It puts the power, if you're looking at like iOS in general, from Xcode in your hands, for better or worse.
Yeah.
You know?
Yeah, I agree. Well, cool. Is there anything else that we haven't touched on? So I think definitely I know we had a deep rabbit hole there into the caching. I could talk about it all day, but in terms of rules iOS, are there any other big roadmap items worth talking about? Like call for contributions, definitely I want to get to that. Are there any good getting started issues for people to take a look at? Like what's the status there?
Absolutely. So I think in general, we love to see PRs coming in and fixes. And I mean, you can build an iPhone app with Rules iOS pretty easily. It should just work. If you go into the test directory in Rules iOS, you're going to see like a handful of apps, so many use cases I exemplified, and you can just use iOS, use that Xcode project rule, and LLDB is going to work for you. It's going to compile mixed modules. You can set a breakpoint on it, and you can hook it up to Flare or like a CDN. And it's just going to work. I mean, I feel like we've gotten it to like a pretty good MVP at this point. I think the next things that I'm pretty excited about are making the rest of the features in Xcode actually work without having to build it with Xcode. I'm like excited about that possibility. And yeah, the other one is making it work with other kinds of ecosystems and rule sets as well. I'm excited about that as well. And I mean, that's generally the gist of it. We definitely love to see PRs coming in, and making the CI a lot more robust is kind of like some of the stuff that I've been working on recently, like adding more of the use cases that I have to Rules iOS to make sure that if a PR comes in, that it's just going to work. I think that's the other thing about rules iOS that you'll find is pretty cool is that because most of use cases that people care about are in the tests, so we can merge PRs without worrying about breaking someone else's thing.
Yeah, it's critical. That's awesome.
Yeah.
Good. Yeah, it's good to have those test cases. Awesome. And then I guess one other item that I just remembered, I know in the past there was a little bit of talk of some of the performance implications and overhead, and I think you've probably solved most of these. Is there anything worth touching on there? I know there was kind of like a few optimizations that you were doing on maybe something like the VFS overlay or something like that.
Yeah, so it's definitely like a known issue that if you give the compiler so many search paths, it's going to be slow because it has to look at all of them. So basically, we have a feature in Rules iOS that takes the entire build graph and puts it into an in-memory file system. And then the client and Swift compiler read from our in-memory file system. And effectively, this is how all the tools run. They don't really run off the actual file system. It's called virtual frameworks, the feature. If you look in the repo, you'll find it. But basically what this does is this drives the entire tooling around an iOS build from a file system that is created by Bazel. And we do so in memory right now. And that effectively makes builds a lot faster just by like having an effective file system representation that the Swift compiler and client compiler work directly with. So everything can compile as a framework, and there's no frameworks on the file system at all. So if you had a CocoaPods build that was compiling its frameworks, that has like special implications in the Swift compiler and in the client compiler about how that's treated. The problem with it is that in Bazel, you had to have an include path for all the frameworks. So what we did is we put those into an in-memory file system, all these frameworks, and the source code doesn't actually move around at all on the file system. The file system in memory just maps down to the source paths.
Right. And this is a somewhat recent addition, I take it, that was implemented as a performance optimization after some complaints.
Yeah, I mean, it was effectively like around parity with like what CocoaPods would do to it, but then this made it like way faster. And you have to turn it on. It's not on by default. I think in the future, it might actually be the only way to do it because the other way is just not a great result to do it the other way. And I'm really stoked about how it turned out. I wish we could have header maps effectively doing virtual file systems. Like I wish that data structure was implemented in a header map, binary data structure, and that thing could just like memory map it in. But it has to publish JSON. It is what it is. Those JSON files, they can have like all kinds of dependencies in there, and it's pretty negligible for the Swift compiler and client to read them in. So it's not a big deal. The other thing that I think in general is not 100% nailed down yet. Oh yeah, the indexing support is another interesting thing too about how we like pretty much like changed how like indexing was working inside of Rules Swift and Rules iOS together so that we could effectively remotely index the source code as well.
Yeah. We actually kind of completely glaze over indexing. So obviously there's a few different. Yeah, we should definitely call some things out here. So there's a tool from what Lyft originally, Index Import, that a lot of folks should be somewhat familiar with if they try to get into getting indexing actually working with Bazel, right? So that's some of the older existing stuff. So obviously you had probably one implementation of indexing in XCHammer. I don't remember if you're using Index Import or not. I don't think you were, right? And then now there's in your current implementation probably yet another solution. So maybe give us just a quick run through it as we wrap up here, kind of pushing our time. Maybe it's a quick overview of indexing and how it works so well today in your implementation.
Rules iOS, yeah. So basically, the problem is that by default, the compiler was indexing everything in a mixed module. So if you had, and Bazel had to have an index store per library, per module, effectively. And so it was an M times N problem where M was the number of headers that you had and N was the number of dependencies you had. So this thing was literally creating over 20 gigabytes of indexer data in the file system, which was just crazily slow, and it wasn't compatible with like mixed modules and like caching and Objective-C. So what we did was we effectively, inside of the Swift action, when it compiles Swift, we have an index store that's shared on the worker so that your worker has its own cache. And then we export a subset of that index for the output files in the compiler invocation. And then we write those to the CDN. And then index import integrates those. There's another issue to actually read out these indexes directly from Bazel and emit the output into Xcode. That's like the final thing, but the current status of it is that it plugs everything back into Xcode with index import still,
Okay.
because it has to map the file paths. But
Right.
there's a GitHub issue for it, but making like Swift compiler and Clang compiler work with remote caching and Bazel has been the underlying theme of all this work, really. Like, the debugger used to work with it. Now, the last problem that we have to fix is the Swift modules, and the precompiled Clang modules need to actually be updated a little bit to work with remote execution and remote builds so that we can express these things a little bit better, these Clang modules. But I don't want to ruin any spoilers or like talk about things that are not in existence, but I think there's still like some pretty interesting work to do in Swift and Clang compilation to make it work better with remote caching and Bazel. But we've definitely got like a lot of the problems fixed in Rules iOS.
Great. That's awesome. Well, cool. And so definitely let's maybe toss out the repo. I guess, what's the URL for folks to find it if they're not aware of it?
It is github.com/Bazel-iOS rules_iOS. And that is the easiest way to build an iPhone app in Xcode, or excuse me, that worked in Xcode with Bazel and supports mixed modules. Love contributions, love PRs, issues. And thanks so much for putting this together. This is like so cool. I'm really excited about your offering from Flare. I'd love to hear more about it. We should talk more about it offline. And it's super cool. Like, I can't believe how far we've came like as an industry. I feel like it was maybe like 3 years ago that Bazel really ate iOS development in the industry, and now everyone's kind of using it. So
yeah, it's awesome. Well, Jerry, always a blast to talk to you. Yeah, we'll go ahead and wrap it up here. I think we're kind of gone over our time quite a bit, so let's go ahead and close it out. Yeah, thanks.
Cool. Good talking, Zach. Catch you later.
Thank you for tuning in to the Flare Build podcast. Please like, subscribe, and tune in again with Zach and Tatiana for the next podcast in the series.